Welcome to an example in which we're going to do a goodness of fit test. Here's the story. A recent national report states that the marital status distribution of the male population age 18 or older is as follows. So this is the men 18 or older in the nation. Never married, 31%. Married, 56.6%. Widowed, 2.1%. Divorced, 10.3%. So the table below shows the results of a random sample of 1,876 adult men from California. Test the claim that the distribution from California is as expected at the alpha 0.01 significance level. What are they saying? They're saying test the claim that the California is as expected, meaning fits that California data, let me back up here, California data, the California survey, the California survey of whatever it is, 1876 men, fits the U.S. percentages. That's what they're saying. Fits. It's a goodness. So down here we'll choose goodness of fit test. So you see the idea? They're wondering, are California men about the same percentages as men in the nation? You know, if never married is 31% of the men in the nation, and married is 56.6%, and widowed is 2.1%, and divorced is 10.3%. They surveyed 1,876 men. Here's the number they found that were never married out of that 1876. And this is the number married, widowed, divorced. They're saying, do these percentages fit the percentages for the nation, this California survey? Does it fit the numbers for the United States? Is California men just like the rest of the United States? Do they fit? That's the question. How do we test it? Well, I gave you notes. Let me go there and find them for you. I'm going to find the exam for notes, which are somewhere. There we go. All right, here they are, the exam for notes. If you go on down to number 9, there is a goodness of fit test. Is. I'll bring it over for you, and I'm going to insert it down here so we can have it quickly and easily. There we go. Goodness of fit test. So what does it say we do on a goodness of fit test? Well, first off, it says that the null hypothesis is that observed and expected data fit each other well. So the California data, which is observed, and the expected data, which is the percentages for the whole United States, they fit each other well, or they don't fit each other well. Okay, so that's what we'll do down here. So for HO is the same. There it is. The distribution for California is the same as the nation, right? Fits, same. And then the H1 is not the same. California is not the same as the nation. Does not fit the percents. This is fits the percentages. So that's what we're talking about. Does the survey that we did for California, the 1,876 men, do the percentages fit? Well, let's figure it out. How do we do it? What we're going to do, coming on down here to the notes again, goodness of fit test. We're going to put the observed values in L1, and we're going to calculate the expected values and put them in L2. How so? Well, if it said equal frequency, you would do this, but it doesn't say equal frequency. If there's category percents listed, that's what we have, right? Category percents are listed. Each category percent is multiplied by the total number of values. Each category by the total number of values. So we got to come up here, and we've got to do that for L1 and L2. Okay, so this is L1, so put these guys in L1 in your calculator. Now L2, it's going to be each percentage, so I'm going to take like 31% for the never married. This is never married. So 0.31, right? That's the decimal version of 31%, times the total number, which is 1876. So, and use your calculator. And I just did, and I'm getting 581.56, but it says round to the nearest whole number. So that means 582. So what we're saying then is that if in the nation, 31% of the men 18 and older have never been married. So if the California data fits with that, we would expect, these are expected frequencies, if the California percentages are going to come out the same, we would expect that 31% of, remember times is of, 31% of the 1876 men that we surveyed, right? The 1876 adult men from California that we surveyed, random sample. 31% of times the 1876 men, which is 582 men. We'd expect about 582 men in our sample would be never married. How many did we actually get? 578. That's pretty close. We would expect 578. We got 582. Pretty close. All right. Let's keep going. Next group, married. 0.566 times 1083. I'm getting 612.978, which again we got round to a whole number, they told us. 613. So we'd expect 613 men to be, did I do that right? Times 10. Oh, not 1083. What am I doing? This 1870. Where did I get 1083? Oh, I grabbed this number. That's not right. Times 8, you're always supposed to multiply by the whole amount, right? That's what it says down here in the formula. It says each category percentage multiplied by total number of values. I was messing up. Let's try that again. 0.566 times 1876, and we get 1061.82 or 816. But we round it to this whole number. 1062, right? 1062, which is pretty close to 1083. So, yeah, it's coming out close to what we would expect. Next group, widowed, 2.1%. Change it to a decimal, always move it back 2 places. And times 1876. I'm getting 39.396, round to the nearest whole number again, 39. So that one came out a little different. We expected only 19 men. We expected 39. 39 men are widowed, but we only got 19 was what actually happened. So that's a little different. So next one, last category, divorced. 0.103, 10.3%, move the decimal back 2 places, times the total amount. We're saying 10.3% of the whole group of the 1876 men surveyed. So 10.3% of the whole group is 193.228, which rounds to be 193 men. So we would expect, these are all what we would expect. If the percentages were the same, if 10.3% of the whole nation of men in the whole nation are divorced, then 10.3% of times our whole sample, we'd expect to get 193 men in our sample that are divorced. We actually had 196. That's pretty darn close. So they all fit except for this number. This number's off a little bit, right? 2.1% of the nation men are widowed. So 2.1% of our sample, we would expect 39 men to be widowed, but we only got 19 when we surveyed our men. So that seems a little low, but otherwise it's a pretty good fit. So now we're going to figure out the actual number. How do we do it? Going down here. So we've got the, oh, by the way, I should say this. So make sure when you do L2 over here that you actually, so these are the, so put these numbers right here in L2. And L1 is those numbers. So whenever, and because they said round. So if they say round, you've got to put in the rounded numbers you can't put in the original. Some of the other questions on goodness of fit will not say anything about rounding. And if that's the case, just type this formula straight into L2. These formulas straight into L2, and then just leave those decimal answers that you get. Don't round. So if they don't say anything about rounding, just type the formula straight into L2 and leave the decimal numbers. If they don't speak of rounding, just leave the decimals. But this one said round, so I have to round, and those are my L2 values. And these are the L1, so put those in L1 and L2, and then go to your old calculator. And what do they say to do next? For the TI-84, you do stat test, x squared or chi-squared goodness of fit test, like that. TI-83, do that. Oh, I forgot about degrees of freedom. Over here, degrees of freedom is number of this is degrees of freedom. It's number of categories minus 1. So we got to go back up here and say, oh, okay. So that's right down here. Number of categories. How many categories do we have here? 4 categories, right? So then the degrees of freedom here is 4 minus 1. 3. 3 degrees of freedom. All right, and now they want the other information. So how do we get it? So we go to our calculator, and on the, I have a TI-84, so I'm just going to write that first. So the TI-84, we hit stat, go over to tests, go down to D, which is chi-squared goodness of fit test. And hit enter. And then when you do, it's going to give you some questions. It's going to say observed, and expected. So observed and expected. So this is L1, L2. It's just asking where's your list of observed values, where's your list of expected values. We put our right here. This is our observed. This first frequency is what we observed. This is what we saw. And this is over here expected. So L1 is the observed, L2 is the expected. And it'll probably already have that in your calculator. Degrees of freedom was 3 right there. And hit the buttons, calculate it. Now if you have a TI-83, I don't know where to write it. I'm kind of running out of room everywhere. So this, let me squeeze this over here. This was TI-84. If you happen to have a TI-83, I'll go down here. If you have a TI-83, it's easier. You just hit the program button, which is right underneath the stat button, and you have that program that you typed in. I sent everybody the link for that, and you do the I think it's GOF test, and then you just choose that, and it'll do it for you. All right, so when you do that, here's the numbers I'm getting. This is the x squared thing here, which is really chi squared. It's 7.107 rounded to 3 places, and then it asks for the p-value to 4 places. I'm getting 0.0686. 0.0686 rounded to 4 places. All right, so then the big question is always about the p-value, right? That's the big deal. So the p-value, 0.0686, compared to the alpha significance level. What was our alpha significance level? Oh, right there. Alpha significance, 0.01. So 0.01. So the question is the alpha level bigger or smaller? Well, that's clearly bigger, isn't it? 0.06 is bigger than 0.01. So if the alpha, what does that mean? So we have our very important saying, if the p is low, HO must go away. Right? If the p is low, the null must go. If the p is low, the null must go. That's our saying. If the p is low, the null must go. So, is the P low? No. Our P is not low, it's greater, right? Our P is not low, it's greater. Greater is big, it's not low. So therefore we got to put a not here as well. So remember how that statement works. The P value being greater or less will tell you whether which one you accept, because we're trying to say it's either going to be HO or it's going to be H1. Which one are we gonna keep? It's like two attorneys arguing in a court of law. We're either going to say guilty or innocent. We're going to go with one attorney or the other. How do you know which one? Well, it's all about the p-value. If the p-value is greater, like ours is, then you take that statement we always say, if the p is low, the null must go. But you put it not, because this p is greater, it's not low. If the p is not low, then the null must not go. If the null does not go away, that means we're keeping the null. And right here, that means we fail to reject the null. I think they just write the word null. Right? Because we're keeping it. We're not rejecting it. It must not go away. Right? If the P is not low, the null does not go away. So what does that mean? We're keeping the null. So that tells you which one you want. You want to keep the null, this one. Here, let me back that up and put a nice container around it. There we go. There's the one we're keeping. We're keeping the null, and we're rejecting the other one, aren't we? Is that making good sense? That's how you know. On all hypothesis tests, it's always about the p-value. If the p-value, now if that p-value was less, right, if this alpha over here was something like 0.09 or something, then 6 would be lower than 9. So if the p was lower, if the p is low, the null must go. I would cross out the null. I would reject the null. Right? If the p is low, the null must go away and reject it. I would say no to the null, and I would keep the h1 in that case. See the difference? So if the p was low, if the p is low, the null must go. Get rid of the null, reject the null, go up here and cross out the null, keep the h1. But we had the opposite. We had the p greater than alpha. 0.06 is greater than 0.01, so it's not low, it's greater, it's not low, so the HO must not go away, keep the HO, so we keep the HO and get rid of the other one, and that means if we're keeping the HO, we fail to reject the null. And then that'll tell us how to answer the final question also, because just go back up here, which one are we keeping? This one. Now remember how the data goes? The evidence, this is always, whoops, I wanted a different color there for clarity. This is always weak evidence. The HO. Now the H1, to conclude H1, always requires strong evidence, and which we didn't have. That's why we didn't go with H1. So since we're going with HO, right, that's the one we're concluding, then that means evidence is weak on this problem. Evidence is weak. To see how we did that, again, one more time. So the p-value is greater than the alpha. 0.06 is greater than 0.01. So the p is not low, so the null must not go away. The null is not going away, we're keeping the null. So when you're keeping the null, getting rid of the other one, that means weak evidence, because weak evidence is always for the null, strong evidence is always for H1. So we're keeping the null, so that means evidence must be weak. We must have weak evidence in this case. So let's go down to the answers and see what we can see. There is insufficient evidence. That means weak. Insufficient means not enough, right? So they're saying not enough evidence. Insufficient evidence. That's right. That's right. How about this one? Insufficient. Yeah, that's right also. Weak evidence. Insufficient. Not this one, not this one, not that one, right? Because those all say sufficient evidence. That's not right. There was insufficient evidence. There was not enough evidence. So, all right. So now, but there's two options. Which one is it? Let's try reading the rest of this one. to conclude that the distribution of marital, there's not enough evidence to conclude that the distribution of marital status in California is not the same as it is nationally. Yeah, that's exactly right. What do you mean? How am I doing that? Well, look what we're concluding here. We went with HO, right? HO was our conclusion. Evidence was weak, and what does HO say? This right here is the same. California is the same as the nation. The percentages fit. They're close enough to the same. That's what we're concluding. They're basically the same. The survey we did of the 1,876 men in California came out pretty close to the percentages for the whole nation. It is the same, basically the same. It fits. Well, that's what this says. There's not enough, it says it kind of tricky though. There's not enough evidence to conclude that it's not the same. You see, that's a double not. There's not enough evidence to say it's not the same. So what does that mean? California is, California, okay, yeah, I'm a little tired of that. Let's go. California is the same as the United States, right? There's not enough evidence to conclude that it's not the same. So we say it is the same. That's what they're saying, which is exactly what HO said. It is the same. The other one's not right because it's saying insufficient, dependent. That's not what we're talking about. That's something different. So there we go.